Greetings, everybody. So we are continuing our videos on cost-based image encryption, and the topic of today's video is going to be key sensitivity. Okay, so let me remind everybody again, we are talking about symmetric encryption. So we are using a chaotic system as our source of high entropy. We are using it to encrypt some sort of information signal, then safely transmit it through a communication channel. And back at the receiver end, we are using the exact same chaotic system with the exact same key values and the exact same initial conditions and parameters. And we are reversing the process to obtain the original plaintext signal back. Okay, the classic operations, of course, are shuffling and substitution. Okay, you can see the previous videos where we describe them in detail. So let me remind everybody about the key space and the key values. Okay, for this symmetric encryption, the key values constitute the parameters of the chaotic system. Okay, so let's say, for example, I'm using the logistic map to encrypt the signal. This means that my key values is the parameter of the map R and the initial condition x0. Okay, so we have two different keys here. Okay, of course, the higher the amount of keys that we have, the highest the key space is going to be. Okay, so what is key sensitivity? Key sensitivity refers to the fact that the receiver should know the exact values of the keys in order to successfully decrypt the signal. Okay, so ideally, actually, not ideally, axiomatically, it should always hold. If the receiver doesn't have the exact values of the keys, the decryption should fail. Okay, so is this possible in this situation where we are using chaotic maps? Yes, this is actually possible, and the reason this is possible is because, as you all know, of course, chaotic systems have this sort of butterfly effect, which is the sensitivity to parameter changes. So here, for example, I have the logistic map and I slightly change the initial value of the key, x0, and after some iterations, the two time series diverge completely. Okay, here it takes around 50 iterations for the time series to diverge, but different maps have even higher sensitivity. So in some other maps, this may happen in just a few iterations. You don't even have to wait that long. And of course, ideally, this should happen with respect to all key values. Okay, so here I change the initial condition, but the logistic map, as we said, has two actually key values, x0 and r. If I changed r slightly, the same result would happen. Okay, so again, changing r would result in the same butterfly effect. If I'm using some other map that has not one or two or three or four parameters, this butterfly effect should appear with respect to all parameter changes. Okay, so when I'm using a different chaotic map, all changes in every single parameter should result into this sort of butterfly effect. Okay, so just because the map has this, butterfly effect, the whole encryption design pretty much inherits the same butterfly effect. Okay, so if I change some sort of keys to encrypt the signal, this sort of avalanche effect will happen due to the encryption process. Okay, so this is the idea actually behind using chaotic maps for encryption. Okay, because slight changes in the keys will change the time series, so they will change the encryption, so the decryption will fail unless you know the exact values of the keys. Okay, this is what happens here. I'm giving you one example where I have actually encrypted the paper's image. And here I have a very complex process. I will put the link to the paper in the description. And in that paper, we are using multiple chaotic maps to encrypt the signal. So every possible change that I can make into one of the key parameters of these maps results in a failure. So all of these messed up images that you see here are actually examples of decryption with the wrong key values. So key sensitivity for this example works perfectly, right? And this should happen in all cases. Here I have another example where we are encrypting curves. In the first example, we are encrypting this G curve right here. And in the bottom example, we are encrypting this teapot surface. Okay. And this is the original files. In the middle, you see the encrypted ones. And on the right, you see the decrypted ones with wrong keys. So Obviously, we have a failure because the decryption is not equal to the encryption, to the plain text, I'm sorry. So here, for example, the decrypted curve has nothing to do with the G symbol. And again, here, the decrypted surfaces have nothing to do with the original teapot. So again, slight change of the parameters will result in a failure in the decryption. Okay. And the third example of key sensitivity, this is from another paper. I'm going to put it in the description as well. It's from another video actually that we're going to make. It's about a chaotic password generator. So here we're inputting some keys and we're generating a random password chaotically. Okay. And I have some examples where changing one slight value of the keys also results in a different password. So this, for example, are the initial keys for the chaotic password. And here I have one slight change. Instead of Smith in the mother's family name, I write Smiths, and this results in a different password. Okay, so key sensitivity. And again, I change slightly the key of the username. Instead of Jane Doe, I use John W. Doe, so it's a typo. And again, this results in a different password. Okay, so in all of these situations, practically, you see the key sensitivity of the chaotic system, which is inherited in the encryption process. Okay, so this should always be the case. Okay, so you should always have key sensitivity in any design that is based on chaotic systems. If you don't have a good key sensitivity, probably you need to improve your design, right? So thank you very much, and I'll see you in the next video.